Andrea Montanari from Stanford University, who's going to talk about from overparametrized neural networks to harmonic regressions. Before giving you the floor, though, I'd like to let you know a little bit more information about Andrea. So he is a recipient of the Massey Award from the IT Society, the Information Theory Society, in 2016, and he also obtained the LeCun Prize from the French Statistical Society just about 2 years ago, 2020. He was an invited speaker at the ICM in 2020, and IMS Medallion Lecturer in the 2020 Bernoulli IMS World Congress. So, Andrea, the floor is yours. Thank you for coming.
Thanks very much for the invitation. Thanks to everybody for showing up. And yeah, I'm very honored to give this presentation. And let's see how the switch works. I don't know how the switch works. This is supposed to go here.
It's not working at all. I think okay, so this one is working. Let me just double check on this one. Yeah.
How do I do next page?
I'd imagine.
Oh, okay. Okay, so this is joint work with yeah, Beruz, who is so he's a former student of mine, and Song and Theodore. Song is now in Berkeley, Beruz at Google, Ichao is at Wisconsin. Okay, I'll start with an appetizer. This is really elementary for all of you, but I think it's good for setting the stage. And the appetizer is the following. Suppose that I have a signal on 0 to pi. This is my signal. And I sample at random points. I sample at random times t1 to tn. And now I would like to reconstruct or represent this signal. Okay, so we are in a Fourier conference, so we'll use Fourier series, of course. This is the Fourier series. I have to estimate the coefficients. And okay, one way to estimate the coefficients is the following. I will try to solve an optimization problem in which I minimize the error at the sampled times. And I want to add a penalty that regularizes my reconstruction. And I'll add a penalty that is a coefficient times weighted to norm of the signals of the coefficients, and I'll take these weights, right? So basically frequency square. Okay, this is a perfectly reasonable way to find the Fourier coefficients. And in particular, I'll take lambda very close to 0. If I take lambda very close to 0, I will get an interpolation of my signal. And throughout the talk, I'll be interested in this regime in which I nearly interpolate my signal. Okay, does this make sense to everybody? This is as reasonable a method as anything else. I don't claim that this is particularly good. It's just one little experiment. I do this and I get the green curve. Right, so it interpolates the points as promised and reconstructs the blue curve. Okay, so now the question that I want to ask is what happens if I add noise, right? So here I added Gaussian noise on all my sample data, and I'm gonna repeat the same exercise, right? I'm gonna minimize the same cost and find a near interpolator. Right? So this is the kind of object that you get. You pass through the points, and you try to be, basically close to linear outside the sample points and as regular as you can. And as you see already from this curve, you are not doing particularly well, right? You are going all around, and if you want to really drive this point home, we repeat the same experiment for many sample size. This is the figure that I showed you before. This is for fewer points, and this is for many more points. Looks like a Christmas tree, very nice, but this doesn't look like a good method, right? In particular, it doesn't seem to improve as I sample more and more points. Something that you would like to do is to achieve is that as the points, the sample size goes to infinity, at least you are able to average out the noise. And in this case, doesn't work. And of course, I can look at it in Fourier basis, and this is the absolute value of the Fourier transform. And the blue is the true signal, and the green is the reconstructed one. And you know, for the three different cases. And as you see, you know, as the sample size increases, I'm able to reconstruct the first few Fourier coefficients as you know, sample size increases. But then I had the noise. I hit the noise floor, and I cannot push beyond that, right? And so this is something that we will see. You know, it's a good intuition. That is given by Fourier analysis, that there is at high frequency there is a floor that you hit, but you're able to reconstruct the low frequency coefficients. Okay, so in fact it's easy to understand that the error cannot vanish as n to infinity, and one way that I think it's very intuitive to you know, understand why it cannot vanish is the following. My reconstruction is such that you know, the reconstructed function has some smoothness. Basically, I penalize the Fourier coefficients by the frequency of the Fourier coefficient. So the reconstructed signal is smooth or continuous, etc. Near the training points, it will be interpolate. At the training point, it will be interpolating. And therefore, near training point, it will be off by a factor tau, where tau is the standard deviation of the noise, right? So if this is my real curve, here my sampled points. Near the sampled points, so this will be away from the true curve by truth signal by tau, where tau is the standard deviation of the noise, and my interpolating curve will be away. And therefore, if I now look at a new test point here, okay, if you look at the L2 distance, this will pick up a big amount because of this. Okay, so in the context of RKHS, this kind of argument is in a paper of Rachlin and Jai. And in fact, in our later experiment, we can witness this. This is the L2 reconstruction error of the signal by this near interpolator. In the noiseless case, you see that it goes nicely down with the sample size. In the noisy case, it doesn't go down. It doesn't average out the noise. Right? So this is very basic and should be no surprise to you. So is there any question? Fantastic. Okay, so the question that I'm going to ask at high level is the following. What happens if instead in doing this exercise in one dimension, I do it in high dimension? Okay, and high dimension throughout the talk will mean that the dimension is a polynomial power of the sample size, or vice versa, the sample size is a polynomial power of the dimension. Okay, so this is the outline of the talk. I'll try to discuss why I'm interested in this high dimensional regime and near interpolators, and some phenomena that arise in machine learning, try to explain this phenomenon, and then the basic results. Okay, so the setting, the real problems that I'm interested in are machine learning or supervised learning problems. In this case, we have data pairs that are as usual responses yi and feature vectors xi, and the xi lives in d dimensions. And so the yi are also labels, and I want to predict new labels. So I want to find out a model, a function that goes from Rd to R. And the objective is that I, given a loss function, okay, I call it dist here really, from R to R times R to R, I want to minimize the expectation of this distance at a new test point. So I sample a new test point y nu x nu from the same distribution. I take a new data point, and I want to minimize really the expectation of this at the new test point with respect to f. And all that I'm given is the sample, right? So I want to find out a model that minimizes the expectation, the expected loss at the new test point. In fact, throughout the talk, I will focus on very simple loss, that is square loss. So I want to minimize the square loss. Okay, the expected square loss. I omitted here the expectation, that is a typo. Does this make sense to you? And the model that I'll assume throughout the talk is that the data points, this is the standard model in statistical learning, the data points are IID samples from a common distribution on R times RD. So the Y are one-dimensional and the Xi are d-dimensional. Okay, and again, I want to minimize this. That this is the test error. I'll call this also the test error or the population risk. Okay, so now, people try to do this by looking over classes of functions f that are, very rich. And of course, one example to keep in mind, even if we will not work necessarily with this, but one example to keep in mind is multi-layer neural networks. So very complicated model with a lot of parameters that are very nonlinear and are, basically compositions of nonlinear functions and matrix vector multiplication. So these are parametric families that are parameterized by long sequences of matrices. If it is 1,000 layers neural network with 100 hidden nodes at every layer, this will be 1,000 times 100 square parameters. So you easily get into the millions of parameters range. Okay, and so all of this work was motivated by a sequence of empirical papers that pointed out a very interesting phenomenon that was actually very well known within the practitioners community, the industry, etc. But thanks to this paper, became widely acknowledged also in the academic community, and is the fact that these models are often trained at near interpolation. Okay, so this is from a paper by Natis Rebro's group a few years ago. And what they did is they took, in this case, very small data sets, MNIST and CIFAR10. So these are image recognition data. And what they trained is that they trained just a neural network with one hidden layer. So really the simplest model that you can think of. And then what they did is that they plotted as a function of the number of hidden units. So this is the width of the network. So this is basically a parameterization of how many parameters has the network. They computed the test error, so the error on unseen data, on fresh data, and the train error, so the error on the data on which you are training your model, the data set which you're minimizing. And what you see here in this plot is that this curve, the train error, hits 0 at a certain point. And this is roughly the point at which the network has as many parameters as data points there are, as the sample size. So the number of parameters is the sample size. And beyond that is 0, right? So it means that your neural network is perfectly interpolating the data. So it's classifying with 0 error on the data that it sees. Despite this, so all of this regime is the regime that we argued before that is a very bad regime to work on. In all of this regime, the test error still keeps going down as you add more and more parameters. Okay. This is another example of this experiment. This is a paper of Zhang et al. Very well known, in which what they did is a different experiment. They took a standard neural network that is at the moment was state of the art, inception, and then they trained on ImageNet, a bigger data set, and they replaced the labels. So the labels corresponds to the image classes by random labels. So these were different type of object, house, dogs, cats, etc. They replaced these image classes by random labels. Okay, and then they fit they repeated the training procedure. They fitted against the neural network as if the labels were not random. And what they observed is that the train error goes to 0 even with random labels. Okay, it takes more time than with the true labels, but still go to 0. So this neural network have enough parameters to memorize the data set, to interpolate the data set. They are trained to a point that they really interpolate the data set. And they have so many more parameters that will be able to interpolate the data set, even if this was white noise. So even if you feed to this network white noise on finitely many data points, it has so many parameters that it fits perfectly the white noise. And this is the regime in which they work. So it's exactly the regime in which we said before you shouldn't, right? Because it's not a good idea. You are not washing out the noise, right? You are not averaging out the noise, and still it works. And this is, you cannot argue that this is happening. The classical way of arguing is that this is perhaps is working because it's a low noise setting. But here they added gradually increasing level of noise. This is the label corruption, and still this whole business works. Okay, so even with noisy data, interpolation in this image classification data gives some non-trivial result. Okay, so when I first heard this, I was flabbergasted, and I remember talking to a student and telling to him, you know, we should try to understand this. And he clearly, a very brilliant student, explained to me, well, no, we shouldn't work on this because this doesn't make any sense. And it was probably, I don't know, but now I think I understand it to some extent. Okay, so what is the picture that I'll start describing the high-level picture, because at the moment can we really make sense of this picture rigorously on some corner, in one corner case really. So I want to first describe the intuition beyond that, the model, and then describe the model. What is the intuition? So this is my cartoon for the space of models, right? P will be the number of parameters of my model. So any model, any function will be given. So this is the number of weights in my neural network. So every point here is a neural network, if you want, and P is the total number of weights. Okay. So theta is collectively the set of weights. And ERM0 is the set of models, so the set of points in this space that achieves training error equals 0. This will be the training error. So this is the fitting error on my sample data, right? And this model, obviously, they are so overparametrized, so P is much larger than the sample size, that this set is non-empty. Not only it's non-empty, but it's very large, it's very high dimensional. So P minus n is very large. So you have a cost function that has, a set of, it's a non-negative cost function that is a set of zeros that is very high dimensional. And here what I'm showing you is the set of zeros of this cost function. So this is what's happening in. Of course, all of these are, from the point of view of training, of fitting error, these are all more or less equivalent points, right? Now, what happens when you train, right? When you train, what happens is that in this model, you start from a random initialization. In the initialize SGD or gradient descent at random. So you start with a random initialization, and then you descend this landscape. You should imagine that here there is a landscape coming up, right? So this, you run gradient descent in this landscape. And perhaps what's happening is that this set of empirical risk minimizer is so large that when you do gradient descent, you are very close to a global minimum, so you converge very rapidly to a local minimum. Okay, so this is a lot of hand waving, right? But this picture can be made rigorous in one specific regime, and this is what's called the linear or neural tangent regime. Okay. And so I want to explain this because, very briefly, because otherwise you don't understand the motivation for what I'm doing, and you think that this is just blubbering. Right? So I want to describe this linear regime, this neural tangent regime, in one specific case that is the simplest that I know, and this will be a 2-layer neural network, right? So it will be a 2-layer neural network. So this is, I take X, I multiply it by first layer weight, I pass it through an activation function that for all the purpose of the talk can be any function. Basically, it has to be square integrable, but anything else is okay. And then I don't even put second layer coefficients. I just combine n of them. Well, one thing I put, half of the second layer coefficient equal to plus alpha and the other half to minus alpha. And you see why I take half to be positive and half to be negative. And the reason is the following. I'll initialize this. My initialization will be that these weights will be isotropic, let's say uniform on the sphere. It doesn't really matter. And the other weights will be just equal to the previous one. Okay, it's a special initialization. It's just to simplify the math. What simplification it implies that at initialization, each unit here cancel exactly one unit here. So at initialization, this model is trivial, is exactly 0. So I'm initializing this thing. It's a random initialization, but as a symmetry such that I initialize with a function exactly 0. Does this make sense? I see some nodding. Okay, so now what I want to do is to say the following. So the intuition for this is, perhaps what's happening again in the overparametrized regime, I move very little, as I described before, and therefore I can linearize this model around its initialization. So I can linearize in the parameters, not in the input, around its initialization. So let's look at a small neighborhood of the initialization θ0. Okay, and I'll scale this small thing, this small perturbation around θ0 by 1 over alpha, and you'll see in a minute why. That is arbitrary, it's just to make things look good. All right, now let's do Taylor expansion in alpha. So you get the first term alpha, and then there is the gradient term where I take the gradient of the model with respect to the parameter, and then there is order alpha minus 1 term. Haha, now comes my special initialization. This is 0, okay? And therefore I get, this is 0. In general, this is not important because this is really a not particularly interesting term, right? Because it doesn't have free parameters. And then there is a term that is b times the gradient of the model with respect to its parameter. So what I'm saying is that perhaps, if really I'm in this overparametrized regime, I can approximate the original model by this linearized model that is just coefficients times the gradient with respect to the parameter of f at initialization. Now, if I take the gradient of my specific neural network, it takes this form, right? If I differentiate this with respect to the theta, I guess theta prime, and then the x comes out. So you get sigma prime, and then the x comes out, and then the coefficients. So this is the neural tangent model for a 2 layers neural network. And this idea really appeared also before in the literature, but it was really driven home by this paper of Jacob, Gabriel, and Ongler. Okay, so I'm just differentiate. This is, by the way, something that is not so you can do for any nonlinear model. So what I'm saying here is that if I believe that this linearization is accurate, then the empirical risk minimization problem, that is minimizing the fitting error. Here, this is the evaluation at the model at the end data point. You can replace it by a model in which I replace this by its quadratic, its linear part. So it becomes a quadratic optimization problem. In other words, if I'm thinking of this as a 3-dimensional, as a landscape in which this is the set of 0, around a neighborhood of the origin, this landscape looks like a parabola with a lot of 0 direction. And this set of 0 looks like an affine space. Okay, so if I zoom up this picture here, I should see something like this in there. Okay, so all of this is not just hand waving. There is at least 20 papers that, or perhaps by now many more than 20, but a certain number of papers that prove theorems of this form, that this is indeed a good approximation of the original problem, provided the model is sufficiently overparametrized. Okay, so if we believe all of this theory, now what we are still left to understand this interpolation business, how comes interpolation works, right? But now we have to, within this linear regime, we have to understand it just within a manageable model. And the manageable model is the following, is this linear model in which I take basically the data, I map them through a featurization map, and then I fit these coefficients. And the featurization map takes this form. And if you do gradient descent in a linear model, now which point it converges to, it will converge to the point of minimum L2 norm, right? If you have gradient descent in this landscape, is very easy to prove that it converges to the 0 here that is closest in L2 norm to the initial condition. Okay, so what I really want to understand is, I have this model, I fit the beta in the overparametrized regime by minimizing L2 norm, I get beta hat, what is the generalization error? Okay, so this is what we want to understand. How comes that the training error is much smaller than the test error, and despite this, test error is small. And what we are, so now if you don't care about motivation, now comes the result. So you can take this as the statement of the problem, right? The statement of the problem is the following. You have data, xi, and you fit them with this min L2 norm method, where the featurization map is a random featurization map that takes this form. And of course, it's natural to generalize this by putting a regularizer as we did before. And what we are interested, the interpolation limit is lambda equal to 0. And what we want to characterize is really the test error. Okay, does this problem now make a little bit of sense? Why is this interesting? So this is really captures what is the generalization error of 2 layers neural network in the neural tangent regime, in this linear regime. Okay, so we studied this in a number of settings, but I'll describe the settings that is on which we understand the most, and that it's the simplest also. And it's the following. I'll take my data to be uniform point in the sphere, very similarly to how before I took them uniform in the interval 0 to pi. And I take the response to be any function of x plus noise. And again, sigma can be pretty much anything as long as it's weakly differentiable. I need to make sense of this sigma prime. And then I'll assume, okay, for stating the result, we have more general result, but for stating the result, I assume that sigma is generic. That is, if you look at its expansion in a Hermite polynomial, all coefficients are non-zero. Okay, so I should emphasize one parameter. Here I have 3 parameters, right? I have 3 dimensions. I have n, lowercase n, this is the sample size. Uppercase n is the number of neurons. And d is the input parameter, input dimension. So the number of parameters here is n times d, right? And my featurization map, you see my featurization map, because each of these is a vector of length d, and I'm taking capital N of them, okay? Or you can see also in the original network, because the original network was something like sum of theta I transpose times x. So each theta I lives in d dimension. There is n of them. Okay, so this is the number of parameters. And okay, so our approach to analyze this problem, or approach that I'll take here, is that I'll first discuss the n going to infinity, the infinite width limit, and then control the difference between finite width and infinite width. Okay, so let me first state these results. So now I want to take, infinite width, and as I said before, now I'll take high dimension. So this means that the sample size is a power of the dimension. Now there is, what I'm doing here is that this ridge regression. Of course, there is a way to view this in function space as kernel ridge regression, in which we are minimizing over all f, and I put an RKHS norm on f. And what is the structure of the RKHS norm? The RKHS norm is the product of the featurization map, and so takes this form, and is a finite rank. It's a rank capital N times D kernel, and it's a random kernel because thetas are random. Now, what happens when capital N to infinity? At least intuitively, this converges to its expectation. It's obvious that it converges pointwise, and let's take there. And this kernel has the form of an inner product kernel, okay? Because here we have an inner product, and here I'm taking theta is isotropic. And this correspondence between this random feature and kernel is something that was studied before. Okay, so now we are looking at this case. So using this correspondence to kernels, this can be precisely analyzed. And this is the first theorem. It says the following. Assume that n, the sample size, is a power of the dimension, and I'll exclude the integer powers for the moment, right? So the exponent in the power has to be away from the integer. Then if lambda is less than a certain threshold, the test error is basically the projection of f star onto polynomials of degree bigger than L. Okay, so what this means, it means that the kernel method is learning exactly the projection of f star onto low degree polynomials. And what is the degree? The degree corresponds to how many parameters, how many samples you have, right? If you have d to the a bit more than d to the L samples, degree L polynomial need d to the L parameters, right? In d dimensions, right? And so, I need at least d to the L samples. And this is saying as soon as I have d to the L plus epsilon samples, I will learn exactly the degree L component of this function, and I will not learn anything about what is beyond. Now, what's interesting is that we also prove, so two things, we also prove that no inner product kernel can do better than this. Okay, so there are a couple of interesting things of this result, but what I emphasize here is that this is saying that this is happening for any lambda small enough. In particular, it happens for lambda equals 0 or 0 plus. So for the interpolating solution. So the interpolating RKHS solution behaves optimally. So the optimal regularization is no regularization in this model. So what's happening here? It happens, of course, that so you have this point in the sphere, and so I'll let me write the white I as distance from the sphere. And now we are fitting a function that passes through all of them. And this is very close. So this is my f hat, if you want. And f hat is very close in L2 sense to a degree L polynomial. This is what this result. But of course, it's not a degree L polynomial, because a degree L polynomial wouldn't be able to fit all these points, right? Because there is many more than D2 at the L. So it has a lot of little spikes, this function. So it's a very smooth function, plus a spiky function, a spiky component. And the spiky component is what allows me to go through all the sample points. So the spiky part interpolates the samples, but is very small in L2. Okay, so this is something that we argued before that cannot happen in one dimension, cannot happen in low dimension in general. But this is exactly what happens in high dimension. And this is the picture of how the risk behaves every time log sample size over log d passes an integer. This drops down. And at each layer, it gets a layer of polynomials, of monomials more. In particular, it says that if, for instance, if n is less than d to the 1.99, you only learn linear function. That is kind of disappointing. Okay, so there was earlier work, a lot of work on RKHS methods, but mostly they looked at, fixed d and rates as n goes to infinity. And there is also lots of work on interpolating models that was more or less simultaneous to ours. In particular, in the context of kernel that was worked by Liang, Rackling, and Zhai, and that got, the results are in the same directions, but technically they are quite different. And okay, I stated the result for the sphere, but in the paper we actually, we got a generalization for general kernels under some hyper-contractivity assumption on the distribution. Now, after our work, just one thing that was left open is what happens when the power of n versus d, the power is exactly an integer. So what happens if the sample size is d to an integer times a constant? Can you blow up here? Can you blow up this step that first I drew as a sketch and I didn't know? Turns out that, okay, my student Theodore was able to get the result, and he got the precise asymptotics for each of these steps. And they have a funny kind of universal shape. Basically, the shape is the same at every step. What changes only are a few form factors, 2 form factors. And it's really, kind of a little bit, a signature of how hot is this area. The fact that he put this paper on the archive in April, and in May there were 2 papers that publish very similar results on the archive. Okay, so this is about the limit of infinite width. What happens at finite width? We want to control the difference and this regime. So one way to think about it is that we want to control the difference between these 2 kernels. Pointwise, this converges to this, but of course, pointwise convergence is not what is important here. And a stronger notion of convergence is some operator non-convergence. So here is an experiment in which, as a function of the width of the network, I plot the minimum eigenvalue of this kernel. Really, this is the empirical kernel. So the empirical kernel will be the kernel on the sample points, right? So here I have finite width and finite number of sample points. I have a sample by sample size matrix, and then I'm looking at the minimum eigenvalue, and this is for different dimension and various sample size. And if you rescale them and you plot them versus the overparametrization ratio, so this is number of parameters divided by sample size, this very nicely, all of these curves fall on the same curve. All right, so this is obviously the important parameters. And this is saying that when all other things are equal, provided the overparametrization is big enough, bigger than a constant, in fact, bigger than 1 appears here, the kernel is pretty insensitive to the sample size and is well conditioned. Okay, so this is one theorem that confirms this. It says the following: if you look at this empirical kernel, and the infinite width version of this, these 2, so now it turns out that this kernel has many different eigenvalues, right? But these 2 are if you so the right way to compare them is not take the difference of the operator norm, but normalize this by k, normalize this by the other. So basically take the ratio of the two matrices in a sense. And this is very close to 1 when the sample size is much bigger than the number of parameters is much bigger than the sample size. So this is the right ratio. And of course, since we are not smart enough, we get some log factors. But as a friend said, what are a few logs between friends? Okay, so now this says that the kernel converges, but the kernel is not the test error. What really matters practically is the test error, right? It's not the operator norm of the kernel. So let's do a simulation of the test error. This is a small experiment which in 20 dimension for this is basically sample size divided by dimension, or log divided by log of dimension, and log of number of parameters divided by dimension. This is the overparametrized regime. So you see that the train error is 0 here, as it should be. The line is the overparametrization ratio threshold. And this is the test error. At the test error, what you see is that it explodes at the overparametrization threshold. And you see that it kind of goes to a limit when you move in this direction quite quickly. So here it becomes flat. And it has this interesting symmetry that I will not talk much about, but there is a symmetry number of parameters and number of samples. This is the same data when I take a slice for constant sample size as a function of number of parameters, and you see this explosion as the overparametrization threshold, and then you go down and you converge quite quickly to this dashed line. What is dashed line is the infinite width limit that you can compute because it's an RKHS problem. Okay, so the second theorem that I'll give you is basically confirming what we are seeing in these experiments. And it's saying the following, I'm assuming again for technical reason always that the sample size is not an integer multiple of the dimension, because otherwise I have to deal with tricky random matrix theory questions, trickier random matrix theory. But if you exclude those cases, those corner cases, then you get the risk, the test error at finite width is equal to the test error at infinite width plus something that goes to 0 with the overparametrization. And the way it goes to 0 is exactly in the right way, right? Is number of parameters over number of samples over number of parameters. So this is saying that when the number of parameters is much bigger than the number of samples, basically I am at the infinite width limit. Then the kernel is controlling. And this is really what I'm seeing in this simulation, right? This is the overparametrization threshold. If I move a constant above, I'm close to the infinite width limit. Okay, so now in particular, so this is what I just said. In particular, what we see from this is that overparametrization doesn't hurt. I can keep add a neuron to my network. This doesn't change the risk, actually. And the figure makes it better. Here, from this result, it's not clear whether the limit is approached from below or from above, but at least it says that it's not stabilizing. And obviously, as a consequence of what I said before about kernel, it also says that interpolation is optimal, because here setting lambda equals 0 is optimal for this piece, and this piece is kind of negligible, right? So interpolation in this highly overparametrized model in high dimension can be optimal. Now, so far I told you all of these that interpolation is optimal basically by saying that it's a consequence of the theorems that I proved or we proved, but I didn't give you any intuition for that. So why regularization is not needed in this high dimensional model? Okay, one intuition is what I gave you before, that you can really, unlike in low dimension, you can really create small spikes. You can have a function that is a sum of a very smooth part and a very spiky part, and the very spiky part can be very small in L2. And this, comes as a natural solution of an RKHS, a kernel ridge regression problem. But there is another intuition, and the other intuition is the following: is that, if you look at the proof, what's happening is that you have these design metrics, the feature metrics, the metrics of regressors, right? So this depends on sigma. You can decompose sigma in a low degree component and a high degree component, very much like you would decompose your features into high frequency and low frequency. And what happens is that the high frequency behave basically as noise. This is very much like you take, a high frequency wave and you sample it at random points, it looks like noise, right? So it's basically the high frequencies, the high degree part of the activation function looks like noise in the feature, adding noise in the features. And noise in the feature are like a diagonal term in the kernel matrix, right? If you take a matrix, a regression matrix, I don't know, A, a design matrix A, and you add epsilon times G, and now you compute the kernel. So call this A tilde. Take your linear measurement matrix, linear measurement operator, right? And you add Gaussian noise everywhere, and now you compute the kernel. This will be the original kernel plus epsilon, G transpose, plus cross term, and the expectation of this is identity, right? So adding noise of the feature is a strict relative, or adding a diagonal term in the kernel, and that's like a ridge regularization. So the high degree components in the activation function basically create a ridge regularization, and that is why you don't need to add any more regularization to this model. Okay, so all of these pictures are consistent with this kind of experiments in which we increase the number of parameters and the error stabilizes to a limit. So it captures a lot of this picture. Now, these are other experiments by Misha, Belkin, and co-authors in which they point out one more interesting phenomenon that happens close to the interpolation threshold. That is, if you really fit carefully the model, you really interpolate, then the test error also has a spike at interpolation. Right? Okay, if you ask Nati that did this simulation, he will tell you that they had this spike also here, but they didn't pay attention to it. And can we understand also the whole curve, right? So far we understand that here it will go to a limit, but can we understand this whole picture? And at the moment we cannot for the neural tangent model, but we can do it for a simpler model. And this is this random feature model that was really popular since this paper of Rahimi and Recht. So this is basically a 2 layers neural network in which I don't train the first layer. So it's again a linear model in which linearly parameterized model in which all the theta I are fixed at random, and I only fit the second layer coefficients. So it's again a featurization map that is given by this first layer, and then I fit the coefficient AI. It's a bit simpler than the previous model, the featurization map. So the math is a bit simpler. Number of parameters in this case is just the number of neurons. So we looked at this model in detail in the limit, which number of neurons, number of samples at dimension go to infinity with fixed aspect ratio. Okay. So in particular, this is a regime in which the overparametrization ratio is of order 1. Remember, we want to zoom near to this thing. So to zoom near that, we need number of parameters over sample to be of order 1. And number of parameters in this case is number of neurons over sample. So we want that ratio to be of order 1. And okay, we'll take also number of sample over dimension order 1. This is not you could take other regimes are also interesting. Okay, so in this limit, we can precisely obtain the limit of the risk. And so the limit will depend on the activation function through the following ratio. So this is the ratio basically of the projection of, here G is a standard Gaussian. So this is the projection of the activation function onto linear function in L2 of Gaussian, and this is the L2 norm of the activation function. So this ratio zeta is really how linear is the activation function. Depends on these two, parameter ratio between, sample size and dimension, network size and dimension, and sample size and dimension. Depend on the regularization, depends on the noise variance, and finally depends on your target function on the linear and non-linear.
So that end of the building, but first, or alternatively, just go down, not that set of stairs, but the next one. So it'll be on your left. Those stairs will come out right.
And we get an explicit expression for this in this limit with two functions. This is the bias and this is the variance. And okay, there is a completely explicit expression for these two functions that I will not write. Is some random matrix theory kind of formula. In some talks I show it, but I have to use a very small font, so I will spare you the very small font. Okay, but these are explicit functions and you can plot them. So the black here is this function, this explicit function, and the dots are simulations for various dimensions, 100, 200, 300. And okay, you really cannot see the difference between, it really matches very well the simulation. And this is for the near interpolating, and this is for a small non-zero regularization, and you really now capture the whole behavior, right? You see the spike, you see that it goes to a limit, and you also see that the spike disappears if the regularization is positive. So now we can, okay, I can pretend that at least in this regime, I really understood a lot of it. I understood this figure now. You can understand also various things, various other things. For instance, one interesting thing is that if you look at this more difficult regime in which everything is proportional, this is the risk, the test error as a function of the regularization parameter. This is for various overparametrization ratio. This is small overparametrization, high overparametrization. The dashed line is infinite overparametrization. So this repeats what I'm saying before, that infinite parametrization is, overparametrization is the best. But also, if you look at the lower envelope of this curve, this is minimized at lambda equals 0. So interpolation is optimal again. But this depends on the SNR of my model. At high SNR, this is what happens. And then there is a phase transition, and at high SNR, you need a positive regularization. So in this trickier regime in which the sample size is proportional to the dimension, that is crucial. So you barely learn linear functions. What happens is that depending on the SNR, there is a phase transition which interpolation can be optimal or needs not to be optimal. Okay, I sped up and I was able to, but I hope that the throughput was not too high. Yeah, so we get, now we understand, at least in this setting, this phenomenon of optimal generalization with minimum of interpolation, and this is captured by the neural tangent model. Yeah, there is a missing, but this, this type of model misses a whole aspect of this neural network that is what people call feature learning. And of course, this is one case in which, doing some mathematics at least helped me, because before doing it, I didn't really believe what I was seeing in the experiment. Now I believe it. Thank you.